smallest possible unit of whatever it is you're measuring. Therefore, in physics, quantum particles are the smallest of the small. First, we have atoms. Then we move into the subatomic realm with protons, neutrons, and electrons. And then we enter the lowest planes of quantum reality, an even smaller state, filled with quarks and leptons, and all of the other most fundamental pieces of existence. Quantum light is light at the photon level. Quantum matter is matter at the same, inimitably tiny base point. From the subatomic downwards, however, the laws of physics bend and break. Thanks to modern technology, scientists can view and measure what happens to some quantum particles. But what they've found seemingly makes very little sense. Quantum entanglement is the primary case in point. In short, it refers to how certain quantum particles can become bound or entangled with one another. This means that when a change happens and is observed in one of them, it's mirrored in its pair. For example, if one quantum particle spins top to bottom, the other spins bottom to top. What's especially strange, however, is that the distance between these particles for this link to happen seemingly doesn't matter, and also that the effect is apparently instantaneous, again irrespective of the distance between the two. The interest surrounding quantum entanglement dates back to the days of Albert Einstein, who famously referred to it as, quote, spooky action at a distance. According to Einstein's then emerging theories on the universe, it's impossible for information to travel faster than light. But quantum entanglement seemingly makes precisely that possible. We know that entangled particles could be split by hundreds of thousands of light years or more, but the instant connection would remain. To some degree, then, it might be said that information is still passed between them. A change to or observation of one would affect the other, and so it would appear that that information will have traveled beyond light speed, thanks to the entanglement. Today, there is still some debate as to whether this is really what's happening, though. For example, some theorize that actually entangled particles are preset and therefore unaffected by whatever happens to the other in its pair. According to this interpretation, information never really travels anywhere. It's more like it's just revealed to us. But that said, there are increasing numbers of experiments and technologies aiming to take advantage of the core principles at play. Perhaps the most eye-catching experiment of recent times came in December 2021 with the so-called quantum tardigrade. A multi-authored and international study was placed up for peer review, claiming to have achieved the first-ever quantum-entangled animal. Tardigrades are well known to anyone with even a passing interest in experimental science. These microscopic creatures are truly incredible and immensely durable. Tardigrades are known to have withstood and survived extreme temperatures and pressures, as well as some of the most challenging environments we know of, including the inner bellies of volcanoes and the otherwise lifeless void of the vacuum of space. In brief, it appears that tardigrades are capable of just shutting down their biologies to essentially ride out whatever existential problems come their way. But the team behind this latest study wanted to go one step further. They wanted to know how tardigrades would cope when even their subatomic makeup was put to the test. In the experiment, 3 tardigrades were frozen down to just above absolute zero, pushing them into their ultra-preservative state from the beginning. Next, however, those frozen tardigrades were positioned between a quantum circuit, generating quantum bits, or qubits. One of those qubits came into contact with and was affected by the tardigrades, before becoming entangled with another separate qubit as well. Over the course of the next 17 days, the team then measured and recorded how changes in one qubit triggered changes in the other, and the tardigrades too. Something of a 3-point entanglement had been created, with the relatively complex and multicellular tardigrades at its heart. At the end of the 17 days, the tardigrades were gradually warmed up and awoken, and while 2 died, 1 survived, leading the experimenters to claim it as the first ever quantum-entangled animal. The study was met with some criticism, however, with many onlookers arguing that the tardigrades had never been truly entangled, that just their close proximity to quantum processes wasn't enough to properly incorporate them into those processes. What's your verdict here? Did that one tardigrade truly go quantum? And had it really become entangled with the qubits running around and through it? The jury's out, but the debate continues to rumble on with some especially heady hypothetical implications. For one, What would or could happen if a similar experiment was ever scaled up? What if human beings were to become quantum entangled in a similar way? Or even, are we already entangled together? We just don't know about it yet. For example, in 2017, the outline for a potentially pioneering study was published, investigating the possible links between human consciousness and the quantum realm. Fronted by the theoretical physicist Lucian Hardy, the idea borrowed from previous experiments looking into quantum entanglement, but further asked, what would happen if human beings were at the center, pulling the strings? Could human beings decide how entangled particles behave without any other input necessary? Elsewhere, similar proposals have led to various other lines of inquiry. For instance, could our thoughts alone trigger changes in entangled particles? And if so, would that mean that we really were capable of ESP-style powers of the mind? Meanwhile, there have also been tentative suggestions made toward using quantum entanglement to explain some other human connections, including love. Science already knows that there is a whole lot of literal chemistry involved in the emergence of love, but strip it even further back, and could our feelings for another person simply be the result of the subatomic binds between us? Perhaps it's not quite so romantic as some of the other explanations for our emotions, but it is still true that underneath it all, we are only atoms. Again, what's your verdict here? Could quantum mechanics really explain such seemingly unknowable topics as the human mind? Or is that just one quantum leap too far? Can even our highest emotions be boiled down into base connections of the subatomic sort? Let us know your thoughts in the comments. In either case, what has become increasingly clear over just the last few years is that the mysteries of quantum science could well prove to be vital to our growing understanding of reality as a whole. More often than not, when quantum physics makes the news, it's closely wrapped up in our ongoing development of quantum computers. And there's little doubt that there is huge potential in this field, with data and processing power like nothing we've ever seen before. But quantum entanglement is still about more than just the qubits of the future fueling faster devices. This is life, the universe, and everything at its most fundamental. This is the bottommost layer of all that we know and see and feel, and also all that we don't know as well. Really, it doesn't get much more exciting than that. It remains to be seen what the final destination will be. Quantum telepathy is one discussed possibility, although it still features almost solely as a science fiction concept only. Quantum mind control is perhaps another route we could head down if researchers can ever prove a kind of hyper-physical link between our thoughts and consciousness. In general, quantum communication could well bridge between here and literally anywhere else in the universe. In all likelihood, then, we're on the brink of another golden age of discovery.